Hi, everyone. Thanks for tuning into our webinar today. We're going to be discussing a couple different topics related around retrofits and uprates for both turbines and generators. Just first, a little background on the two presenters. Myself, I'm Steve T. Reed, Engineering Manager and TG Advisors, part of Entrust Solutions Group in our Power Generation Division. My career prior to joining TGA, I come from an ops and engineering background. I was a plant guy, a lot of different roles. Since joining TGA about seven plus years ago, I've been involved a lot with fleet-wide health assessment programs with our units. I do a lot of analysis work, failure, return to service for customers, as well as new and retrofit design support, QA/QC processes throughout the entire start to finish of the retrofit process. Also here with me today is Tim. Tim, would you like to introduce yourself?
Sure. Yeah, my name is Tim Garner. Been with also with TGA. My former career was with Siemens Energy, all in the generator service business. So generator specialist, then generator manufacturing, and finished with the generator design.
Thanks, Tim. So we're going to start off. It'll be kind of grouped into turbines and generators. And if there are any questions, feel free to send them on in. We'll be able to review those and kind of answer them at the end. Some will be addressed throughout the presentation. So for the turbine side of things, retrofit drivers. So we talk about retrofits, and really uprates are retrofits too. The retrofit goal is typically to take an existing rotor, has some kind of reliability issue, some kind of concern, be it SCC or other things, and produce a new rotor that will meet the life expectations, improve, reset the unit life cycle. The basic retrofit would be a turbine rotor like design, or maybe some design enhancements to improve reliability. Sometimes stationary components are optional. And a lot of other clients, when they talk retrofits, they talk about retrofit uprates, which, can get a little confusing, retrofit versus uprate. But, when you talk about an uprate, the goal of the retrofit process may be justified by an improvement in efficiency or output. And in these instances, when you're doing kind of an uprate retrofit, you're restoring typically both the life cycle due to some kind of issue on the rotor, and you're increasing the performance. So newer designs, blade paths with tapered, twisted designs, tilted stationaries, rotating blades, some section efficiencies can get above 90%. So there's also opportunities to implement new sealing technologies that have come out over the years. The one thing you'll have to note with the uprates, often you're going to have to change the inner casing out and the blading, whereas like the bare bones retrofit would be like in kind, or if you had another OEM come in and scan the rotor and offer a package, it may be a slight twist on the design, but it will fit in the original envelope. So anytime you're doing an uprate, it's important not to forget about the generator also when it comes to the turbine. You got to make sure your generator can handle the output capability increase, and that's definitely a strong consideration. So I'm going to turn it over to Tim to talk a little bit about some of the considerations for generators.
Yeah, so the generator uprate or retrofit is basically to reset the life cycle. So typically, what you're talking about is replacing the stator coils or bars with new, potentially doing a rewind of the rotor, and potentially the exciter as well. So for that, what's your first thing you think about? Do you have hard coils or GVPI design? That'll kind of dictate the scale of what you're looking at doing. Field rewind versus shop rewind. What did your last inspection tell you? Do you have loose wedges? short dielectric strength, loose end windings, rotor turn shorts, L-sit indications, other issues. What the reason you want to know about those when you're going, if you already know you're going into a retrofit, is that they'll also tell you things about some findings you're probably going to see during your inspections or during your rewind retrofit. So like loose wedges, you might see some damage in the slot. L-sit indications, you know you're going to have to do some core repairs. So to give you an idea of some schedule extensions you might end up with. How old's your installation and what's the level of risk you're willing to accept are two other really important questions to consider when you're going into that retrofit. There's always going to be some components that are retained, and there's going to be some components that you replace if needed. So considering your risk, comfort, and how old the installation is really important for that. As far as the uprate goes, the uprate is a retrofit plus. It's all of the considerations for a retrofit plus. There's a few other things to consider. What are your goals? Determining the limiting components. As Steve mentioned, that's a very important part of it. And if you think you're going to uprate your generator and get more power out of it, you need to know for sure what the next weakest link in the turbine train is. So if it could be something as simple as the AVR or some auxiliary component that you wouldn't normally think of, that would be easy to change out and potentially get even more out of the system.
Thanks, Tim. So we're going to jump off into two individual sections, and we're going to go into a little more details about some of the retrofit considerations that you should be aware of during the process. I'll start off with steam turbines, and then after that we'll move back into generators here. So at a high level, what are some of the big ones that you need to be aware of? Axial clearances, that's a big one, especially if you're considering an uprate where you're converting an impulse turbine to a reaction design. And that is because the impulse are a little bit less efficient, but the reaction at the cost of having more efficiency, you have to have more stages because they produce less power per stage. So you would be fitting in that type of conversion a reaction turbine into an impulse setting with a new inner casing, and with all those extra stages that you've added, clearances become even more critical to make sure that they're properly vetted and evaluated. Also, torsional frequencies of the system. We'll talk a little bit more about torsional vibration and frequencies. Blade frequencies, particularly the big blades on the LPN, the really large ones that have lower frequencies that can be multiples of running speed. Bearing pressures, another consideration. Are you going to a larger, heavier rotor? You may need to consider reevaluating the bearing sizes and bearing design. Interface surfaces, you got to consider, you're adding a new rotor, make sure that everything's properly engineered for the coupling interfaces and existing components that are not being replaced. And then also a key one too is don't rely fully on operational data to supplement things in place of calculations. Make sure all the calculations are done and review the design process with the selected OEM or manufacturer. So the first one, I kind of touched on this a little bit, but retrofit axial clearances. So like I said, in impulse designs, you have less stages, but it's a little bit less efficiency. So going for the reaction design turbine, which has more stages, requires you to fit it into the same footprint. So differential expansion is always going to be key with those. You have different components that go into differential expansion. The blades, when you're spinning up to speed, they kind of pull the rotor and shrink it inwards because they're pulling outwards. And then the heating and section of the turbine as it warms up will expand the material. So differential expansion is very important. make sure that due diligence is done during design reviews for clearance evaluations, make sure we're using operating data to supplement and not drive clearance evaluations. And, the important thing to remember here too is, clearance errors. If you have a clearance error on a new retrofit unit, that can result in costly repairs and downtime to address. Those can be pretty costly repairs and damage. The next topic we're going to touch on a little bit is torsional vibration. So for those of you that aren't as familiar with torsional vibration, basically it's a phenomenon that was discovered many years ago, and it occurs when you have a transmission line that's kind of like unevenly loaded. So a generator has three phases or three lines that come out of it, A, B, and C phase, because we have three-phase power. And what can happen is maybe like phase A is at 110 megawatts. Phase B has a bunch of homes on it, and it's 80 megawatts. And then you have phase C is at 100 megawatts, and it has industrial loads. So when you have a large variance of these loading on the generator, you can cause excitation of torsional or double line frequency. In the US, our power grid is 60 hertz, so double line frequency is 120 hertz. And then in the Europe and some other countries, they have a 50 hertz grid, so that's 100 hertz. And so when that occurs and you have that excitation source, it occurs through the air gap. So that's that gap between the stator and the generator rotor, and it will excite certain modes if they are near 120 hertz on the rotor train. So what can occur when that happens is it's high cycle fatigue, so you have a lot of cycles pretty quickly, and we've seen in industry over the many years that this is known, especially early on. There have been big blade failures, blade cracking. We've seen exciter shafts. We've seen keyways, retaining rings, all sorts of issues out of this. So what we do nowadays, there's an ISO standard out there to kind of evaluate. Did you evaluate based on calculations analysis that has a wider margin of error? And then by testing, there's a narrower margin of error. So you figure out your whole rotor train and you say, all right, I'm in the good or the bad zone or the intermediate zone, and depending on where you're at is how you'll treat that during the design process. And that's important. I'll talk about in the next slide when to be concerned about torsional vibration on units. So the other thing to remember too, there is also some low cycle fatigue mechanisms, some additional fatigue mechanisms that can occur both at single and double line. That's the difference. It occurs single and double, so 60 hertz and 120 hertz. Those are typically system transient events that can also excite or be excitation sources at both of those frequencies. So that's short circuits where you have two phases get short circuited together, out of phase synchronization if all the phases aren't in sync when you're going online. Ice storms can sometimes connect two different lines together and cause issues. And then also when there's an issue and a transformer has high speed reclosing event to try to reconnect in. So those can all create torque oscillations in the system as well that aren't good for your unit. So torsional vibration ultimately. So what does this mean for you? You're going through the retrofit or the uprate process. So first of all, you need to understand is your current rotor train, that's your turbine rotor, your generator rotor, are they in the concern zone frequency? Do you have something near 120 hertz? If you're far enough away for the ISO standard, then it's not a current concern for you. There is a trend in the industry to mix OEMs these days, which there's a lot of great OEMs that make a turbine rotor that'll fit into a lot of different packages regardless of OEM. But if you're making big design changes, that can influence where your frequency lies. So you need to do some due diligence and verification around that. Some of the really old units, if you have not had verification of the unit, if you're going through retrofits, you'll want to do that. Sometimes your modeling or assumptions were done many years ago, and they may need to be revisited depending on when the analysis was completed. There's also an increasing trend in the industry on new technologies to rely exclusively on analysis. Remember too that sometimes you do need to do the verification testing, and in torsional that would be a torsional test when you bring the retrofit online if you're in a certain frequency zone. And then generator rewinds and uprates. So if you're making changes to the generator rotor, or you're very close on frequencies, you may want to have some considerations there. And then 1987, units prior to 87. So that's when torsional frequencies were really starting to get understood in the industry amongst all the OEMs. And then the other one too is like if you have a system that's been doesn't have a lot of phase unbalances that would create torsional vibration, and renewables coming on, maybe you're starting to see phase unbalances you didn't have before. So those can also cause issues to arise that you hadn't had in the past. So, especially if you're a same design unit that's had a failure in the industry at another station, things to be aware of. So torsional vibration, very important to understand where you stand and how things will be, affected by the changes from the retrofit process. The other one I want to talk about is the long LP blades. When you're doing a retrofit, a lot of the new designs have different styles of blading, and you need to be aware of blade frequencies and take those into consideration with design changes and redesigns. So some designs can be susceptible to flow-induced vibrations. So you got to consider stuff like harmonic excitations, things that have frequencies that are a multiple of certain speeds. You want to make sure that these blades are tuned to avoid excitation at multiples of operating speed. Also, on freestanding blades, you want to make sure that that you tune them on the big blades. That way, you don't have two blades during manufacturing. There's usually a little bit of tolerance from blade to blade. You don't want to have two of the same frequency, identical frequency next to each other. You want to mix them across the group for those little bit of variances to help prevent the two from interacting together if there is a problem. Non-synchronous vibrations, these are some of your operating conditions. Those are your stall flutter. Stall flutter is a blade vibration phenomenon. It occurs at low load, high back pressure. So you want to understand what's the fleet history, any type of guidance around what are okay and not okay operating zones. You don't want to have a super restricted operating zone based on the redesign. And then unstall flutter, that's a high load, high flow issue, freestanding blades only. So if you're going on a freestanding blade, you want to have some conversations with the OEM around that and the fleet history. So the other thing to know too is I mentioned during torsional vibration, some of the big blades can be susceptible to double line frequency. They can have frequencies in or around that range that can get excited by the torsional vibration if when it's coupled to the rotor, it creates a frequency in that zone. So we have seen industry failures in the past, especially long ago, on blades of these size. So these are all things to vet during the process. And when we talk about these large last stage LP blades, they have a lot more mass. So what ends up happening is, you look at this little quick drawing right here, you got turbine speed on the bottom, okay? Typically, units are operating, unless you have a gearbox system, 3,600 RPM is most of the units out there. And if you divide that by 60, you convert that to hertz or frequency. So 60 hertz system, 3,600 RPM. With this chart, what it's basically showing you is all these H's, 1, 2, 3, 4, 5, 6. These are considered harmonics. So the first harmonic is 60 hertz, the second is 120, 180, so on and so forth. So when we get into these big blades, what ends up happening is the frequencies end up lower down because of their mass, whereas some of the smaller blades have much higher frequencies. They'll be off the chart, potentially, or you may only have one you're dealing with. And we only care about the harmonics up to 6x when we design these blades. So what's important to do is to make sure we have adequate margin between, at running speed, all the harmonics. And then during the startup, and this is also important when you're operating the unit, you don't want to stop at a speed that that overlaps any of these harmonics and the natural frequencies of these blades, any of the multiples, because then you can create a situation where you excite these blades and cause blade vibration. And we can't detect blade vibration in bearings. So blades and redesigns, always want to make sure you understand what you're getting out of the process, what the design is, what's the fleet history, that you're having adequate margin, and asking the right questions through this process. And making sure that you're having tuned last stage blades on freestanding blades. The last one I'm going to talk about here on considerations, and for some of those out there that are looking at retrofits or retrofit uprates, SCC is a big factor in that. When you make the decision to replace the rotor or maybe get some more benefit in output to justify it versus, you know, take the long outage and repair SCC. Stress corrosion cracking is basically it's a phenomenon in steam turbines. It occurs in the wet stages. It is a time-dependent thing, and basically what occurs is when you get to the wet section of the turbine, you'll have any kind of contaminants in the steam, like salts and chlorides, will drop out shortly thereafter, and they can build up in grooves and things in the unit. And depending on a lot of different considerations, from design stresses to the material used in manufacturing, the exact specification, steam chemistry on the unit, can all affect incubation period, how long till you get a crack, and then once you get a crack, it grows really dependent on mostly temperature and yield strength of the material. So something everybody runs into, whether it's, you know, early on in life, you know, 100,000 plus hours, or if it's, you know, 300,000 hours. It can vary quite a bit from unit to unit based on these factors. And incubation is, you know, you inspect. If you're good, you move on. If you have cracking, it's slow growing, you can calculate and continue. The reason we don't really see SCC would be extremely rare in any kind of rotating component like the blades and stuff, is because it has a higher chrome content. You end up replacing blades often before you'd have potential for any SCC to form. So SCC is primarily a rotor issue that we deal with on these retrofits. So what do you need to know from a retrofit standpoint when I'm getting a new rotor to redesign? So what are the best practices? So even if you're doing a like-in-kind replacement, there's always an opportunity to lower peak stresses in the blade attachment area. Lowering these stresses will help reduce your risk of incubation time period. Also, once you have a crack, your ligament width can sometimes dictates how long you have to run before you have to make a repair. So increasing ligament sizes or redesigning this profile can buy you more time in the future when you do have SCC. You can also look at higher chrome materials, although that's kind of limited with integral rotors. You kind of have what the rotor is made of. There's other processes we can do to help potentially extend the incubation periods. One is shot peening. You basically hit the surface of the material and add a compressive layer to counteract some of that effects of the stress at the surface there. And then, you know, do you have an attachment design that's easy to inspect in the future versus one that's very difficult to inspect? You know, all things to consider, and making sure that, you know, you address any warranty language you want to include for SCC. Since that's going to be down the road, you know, that's something that can be overlooked sometimes around warranty language, since it's in the future. And the last topic I'm going to touch on turbines here for considerations is just the shrouded design blades. One of the things that you'll come across in the retrofit process is kind of an industry trend at the moment. A lot of old turbines have the old tenon rivet connection for blading. So you have a shroud that connects several blades in a row together. Basically a small tenon sticks through here, and then you'll get hammered down into a tenon head to secure the shroud in place. The trend in the industry right now is to go towards integral shrouds. So integral shrouds are machined into the blade. They also have some pre-stress on them to maintain contact between blade to blade here. So there are pros and cons to this, which I'll talk about here on this next slide. So drivers, why are you gonna convert? So This eliminates some of the quality concerns around tenon peening. That's going to, you don't no longer have to deal with that. There's also not a surface for corrosion to get trapped under that tenon shroud interface. At the wet stages where you have that precipitation out, that'll be eliminated. Integral blades, you can actually remove them and put them back into the row if they're not damaged. Whereas those tenon connections, if you want to remove a blade here, you have to destructively remove it and often replace blades. There are some techniques to reuse called foxholing, but you cannot do that in all circumstances. Often the shroud material is too thin. You basically machine a little groove in there, restore enough surface to make a new tenon in there, and hammer it back down. There's some other techniques as well, but a lot of times blade removal means destructive process for blade and tenon. Integral shroud doesn't have to deal with that. And then you have to maintain shroud-to-shroud contact for this type of design with the integral shrouds. So it does increase frictional dampening and response to flow-induced vibration factor. So that's another positive out there for the integral shrouds. Now there is a potential problem out there that we've seen a bit of, and one that I want to draw your attention to for considerations during design reviews when converting to integral shrouds. So the blading relies on pre-stress. So these blades are pre-twisted to maintain contact. And when they run up at speed, the blades pull outward centrifugally, and they still have enough, the pre-stress allows them to maintain contact at speed. So what can happen though is you have seals on your blading that run along the shroud on the top. If you have certain designs can be more susceptible than others, but you have really tight clearances where you get a seal rub or rotor deformation going through critical speeds of the rotor, especially when cycling, you can have basically this material, this integral shroud, kind of relax a little bit and lose some of that pre-stress, and that becomes an issue. So some designs are a little more robust than others, and also the clearances and like I said, the rotor deformation are things that impact this as well. So you know, things to talk about, things to review, you know, definitely design considerations. So I'm going to switch on over to Tim now, and he's going to talk about some of the retrofit considerations and upgrade considerations for generators.
Thanks. Yeah, we're going to go through basically component by component and just talk about what to look at for each different thing. So with the Stator core is a really simple, really complicated part of the generator. So made up of a bunch of laminations that are really thin, and they all need to work together to support the coils and move the flux through the machine. So for a retrofit, you want to do as-found testing. The as-found testing prevents the disagreements between the utilities and the suppliers as to the origin of a hotspot. So when you're going through your retrofit, you're going to do periodic LCID or loop tests or ring tests to excite these hotspots, and you want to know if it was there existing. Either way, you have to fix it, so it ultimately doesn't matter. It needs to be fixed, but so depending on the core, the history, the core repairs or modifications should be planned. So if you already know you have hotspots, you really need to plan on repairing those, because you'll never have a better time than when the coils are out. When the coils are in and you try to make repairs, you could end up damaging a coil, and then have to do a partial rewind to repair or replace that coil. So depending on the expected remaining life of the plant, replacing the core is an option. It's not really that common, but it is something that is needed in some cases. The history of cores going out to 80 or 100 years is not there's not really a lot of good history for that. So you're kind of entering into an unknown territory if you wanted to extend your plant life out that far. So the uprate considerations for the uprate, it's a retrofit plus. So it's everything that's included in the retrofit plus a few other things, and the core modifications are a lot more common with an uprate. You might have more load on your rotor, which you could end up with higher end iron heating or body iron heating. Core replacements, like I said, for the retrofit can save time over lengthy repairs. So if you know you have a lot of repairs to make, you could end up chasing repairs for months if if there's an issue. And there is a scientific reason for that, and it's once you make a repair, the flux is going to go and move in a different pattern through the steel. So the electrical steel, once you make that repair, the circulating current might move to the next short, and you don't know how many you have because the one showed up on the LCID or loop test or ring test, and you didn't even know about the other ones. So could end up with long repairs. Another thing to consider when doing an uprate is, can your current core handle the VAR swings that you see daily? So more and more with more renewables on the grid and less rotating mass, large fossil plants becoming less prevalent, you're losing a lot of stability in the grid. So the remaining plants have to take some more of that VAR load that would have been shared among more of that rotating equipment. On the next slide, I have the capability curve, and it shows kind of what I'm talking about. On the curve, you have, this is your limitation for your generator when you're operating. On the vertical axis, you have your VAR loads, and then on the horizontal axis, you have your output, the power that you want to make, because that's what you can sell. And really, the place you want to operate is right on that line. That's, you get the most output, and it's the easiest on the generator to handle. So that's where you make your money. But in a lot of cases, if you have a lot of renewables near your plant or your grid, wherever you are in your area, you don't have a lot of rotating mass, you'll end up having daily VAR swings where you go from negative 100 to 100 megavar. Well, depending on the size of the plant, of course, but at a large plant, you could see as much as 1 to 200 positive to 1 to 200 negative, in a day. So considerations for the stator windings. On a retrofit, you're just going to replace all the windings. That's basically the rewind is there to replace the insulation on the coil. The only way you can do that is by removing it, and when you remove them, they're almost always destroyed. So basically, you just buy new coils or bars and install them. Most of the time, it'll be in kind. Sometimes the new technology has come along and they're upgraded by default. For an uprate, it'll be new windings with whatever new end winding structure that you have. It's, like I said, the upgraded based on current technologies. But in addition to that, you may end up with a higher row bell pattern, which is this picture shown on the right. You may have a different, may have to switch to a different coolant, or you know, at least change the size of the hollow conductors that carry the coolant. For your parallel rings, circuit rings, main leads, and bushings, for the copper, at a minimum, you'll want to re-insulate the copper. In a lot of cases, things like main leads, parallel rings, they can be re-insulated, unless if you have time or budget, then you know getting new copper is the way to go. And the reason is you may not even know you have a history of vibration, because in a lot of cases these components don't have monitors on them. But if you don't notice the dusting and greasing before you go to do the rewind, and it just gets re-insulated, put back in place, that fatigue may already be there. And if those components fail, it's typically catastrophic. It's at least that end of the generator takes a lot of damage. So for bushings, in all cases, you'll want to replace or requalify your high voltage bushings at this time. They typically get forgotten about just because they just work. So in a lot of cases, it's just a forgotten component. But this is a really good time to go ahead and replace those with the overall scope. And that's mostly because it takes a little bit of time to do, and it can be done in parallel with the other work. So you don't have to take another longer than expected outage later on. For the uprate, it's again, just like everything else that I've talked about so far, it's a retrofit plus a few other things, and you have to ensure that if you are going to keep your design or the conductor, you have to make sure that it's going to meet the new rating. Meaning that if you have the same length core, you're not changing the voltage on your machine, which means there's going to be more current going through all the components. So if you get an uprate and you don't change your voltage, you're going to have more current. So that being said, you want to make sure that all of your new conductors or retained conductors can handle that new load. You may want to increase the cooling to it or the cross section, so that it can meet that rating. Rotor windings. So you're going to want to consider a spare. Consider the economics of a spare or new or used rotor that's been rewound for swapping it into the rotation in your fleet. Typically, this is done if you have more than one of the same unit. It becomes a lot more economically viable. And the reason you'd want to do that is a rotor rewind. A rotor rewind can be 50 days, whereas a stator rewind could be 30 days. So that differential there, you'd have to talk to the service provider to discuss what that differential is in order to make that decision. But that differential could make it economically viable to go justify buying an industry spare, which would be a unit from a different plant that's maybe shut down, or a seed rotor from one of the service providers that's already been rewound, and then they put that in and yours goes back into their program. So those are options to consider. For an uprate, an uprate is basically the things you can change are your copper design, so your coolant paths, your cross section, on your windings, and then I think the next slide I talk a little bit about the blower.
Hey Tim, one more thing that may be helpful to add in too is to discuss like GVPI with stators. There may be a similar economic path too on rewinds versus replace or drop in cores. Do you want to talk about that?
Yeah, that's a good point. And so there's, I mentioned in early on that you want to consider whether you have hard coils or GVPI or what. If you have a GVPI machine, the rewind is going to take significantly longer. In some cases, there's a higher risk for core damage. So one thing to consider is the option of replacing just the center section of the stator, or some OEMs offer they'll take the top half off of a small unit and replace the core and the windings as a package. So there's different things that can be done on a GVPI machine that may not make sense on a conventional hard coil machine. But if it's a GVPI machine, there's typical standard rewind becomes a lot more complicated. So for the rotor, blower, and fan, as always, you're going to want to do your NDE. Anytime you take your component, your blower apart, you want to NDE it. Replace with in kind for a normal rewind. Upgrade if there's a service bulletin or a technical letter from an OEM that's notifying you of a known issue, a potential issue. And the reason that you do that is because it seems like a insignificant component. You know, it's moving the coolant gas through the machine, but its location is basically in your end windings. And when one of those fan blades comes off, you'll have to redo your rewind. If you're lucky, that's all. Like it's a pretty catastrophic event potentially if one of them breaks free. During an uprate, you may need to change out with a different design, add additional rows or stages to it. For your exciter, some questions to ask yourself on a retrofit is, what are the conditions of your rings? So if you're doing a stator rewind or a rotor rewind and you have a chance to have an extended outage, you want to look at your excitation system to see if there's anything that you've put off due to schedule considerations that you can do right now. And you know, looking at your rings, maybe your rings are not in the best condition, but we're still operable. It may be a good time to have them skim cut or replaced, or look at your insulators. You know, have you been getting weird readings? And the reason you want to look at things like that is that it may not be immediately needed, but if you can afford to do it now, you could save yourself an unexpected outage for a silly reason, like not a catastrophic event, but just something like your seals are compromised and you have to come down because of hydrogen consumption. So little things like that are good to include in this large scale work because you have the time to do it. Well, most utilities have a refurbishment program for their exciters. The this, like I just mentioned, this might be a good time to do that. For the uprate, can your fan handle it? Can you, there's going to be extra current potentially on your rotor field. And then the last thing for exciters I want to mention was that HIR exciters, they're not new, but they're being talked about again. They were new in the 70s, I believe. But they're being talked about again because of the increased demand for fast response. The AVR is typically for a forgotten about piece of equipment, but at the end of any retrofit or uprate, you'll need to make sure that the curves and different parameters are set correctly. So it's for both a retrofit and uprate. You'll have to do something. For an uprate, you'll probably have new curves and new parameters that you'll have to input there. The hydrant coolers, you always want to clean and pressure test if leaks are found. Make sure you always perform repairs, whether that's capping them or replace the cooler. Cooler leaks can cause insulation failure, and it's never good to go back into operation knowing that you have a potential root cause for your next failure already in place. For an uprate, you may need a larger capacity cooler. You may need to change your flow rate or pumps or things like that, but you'll have to do a study to figure out what, if that is the limiting component, what you would need to do to change that. So in addition to the hydrant cooler, the water cooler on the water skid may need to be increased for an uprate. And always, when you open the system to add new components like windings or whatever, you'll want to do a flush during the recommissioning phase, just to make sure that there's nothing in there, because something small blocking a water tube would cause an increase in temperature at that one spot. And just like a hot spot in the core, an increased temperature in a local spot would still cause accelerated aging of the insulation at that spot and potentially lead to an early failure. So that's all the technical stuff. Now onto the, what do you need to do when you're looking into starting the process? What reviews do you want to make sure you hit? And the bid spec is the first one. You're trying to get together a document to send out for bid, and if you have in-house experts, bring them together. If you don't, get a third party to help you prep that bid spec. Establish the witness points up front. Establish the project completion milestones. Set the design criteria. Your performance guarantees. Correction curves. What you have expectations for there. Any warranty requirements that you have, that any expectations you have for a warranty. Electronic deliverables, that includes things like capability curve and your different curves that you have to input into your control system. NRC design package, if it's nuke, you'll want to make sure you have everything that you need from the supplier that needs to go into that, and you want to include your whatever bonus or penalty clause, liquidated damages that you might have. You want to include that in the bid spec. He's going to go through the next couple slides.
Okay, thanks, Tim. Just going to add a couple quick things to this, which tie into the next section. The bid spec is important because this is where you really set what you want out of this process. And the further you go along, the less chance you have to change or influence what you're getting out of the final product. So making sure you got the witness points you want, making sure that you've agreed to design review schedules, everybody's understands what the performance expectations and other language is. So this kind of perfectly illustrates that when you go through a structured technical review, you come up with an idea, you set the scopes, that's your bid spec, and then you get into the execution phase. So you sent out bids, you got them back, you reviewed them, you selected a supplier. Then you're going to do the formal technical design review. That process is really one of the last stages where you have a lot of influence over the design or what you're getting. And eventually, end of manufacturing, you'll start the install, and then you'll commission the unit and kind of close the project out. So I like this curve because it really illustrates the process. Your biggest time to influence and decide what you want to get the best bang for your buck and what you want to get out of the process to achieve your objectives. It all occurs in the upfront stage. This is really your last influence, and then any influence later on becomes much more costly to change. So I want to make sure everything's clear up front. So design reviews. So what does a design review look like? And this is a checklist from one of ours that we do internally just to give you an idea of the type of questions we ask. So the goal of a design review with the OEM is to sit down and have detailed review. We like to send questions to them around the design criteria, things that are important, so that we can understand and vet any technical risks or project risks or potential changes that we see as, or that jointly agree that are worth pursuing here. So how well are we meeting the design requirements we put out in the spec? We need to vet, are there similar designs? Are we the first one getting this size or style of unit? What's the operating history? What kind of risks, opportunities are there out there still with this design? Have they been benchmarked on similar projects? What analysis were done to dictate some of the design factors and what criteria is being used? An analysis calibrated with test data? Are they based on primarily on calculations? How was it derived, and how are the analysis performed? So off to the left, you can see in our checklist, like this is showing some LP blading questions, like are fundamental frequencies tuned? How are wear issues of integral shroud interfaces accounted for in the design? So on and so forth, service experience, etc. So this is usually a fairly detailed, involved process, and we recommend that everyone go through this process. When you're going through a retrofit, just to understand and make sure that everybody is clear on what you're getting out of it. And this is your last chance to really fully influence the design. And a lot of times coming out of these technical reviews, it would be very rare that design enhancements aren't occurring due to these discussions with the OEM. So definitely recommend going through the process. And once you get through the design review process, now you're into manufacturing. So we're looking at QA, QC checks along the way. You'll typically get informed of like non-conformances as they occur if they impact form, fit, or function of the unit. But also, one of the things you may want to consider in your contract is having in, notification of all NCRs, or when you go on these witness checks, typically you have inspection reports depending on the process you're doing. You want to review the build books that have all the detailed NCRs, because there's no manufacturing process has non-conformance reports, has no non-conformance reports. Some of them are nothing to worry about, and sometimes you may want to do additional engineering to understand if it adds risk or it really doesn't change anything. So typical inspection points we see from our end on the turbine, these are pretty straightforward. Generator rotors, generator stators. A copy of this video is being recorded, so you'll be able to cross-reference this list if you need to in the future. So after the manufacturing process, you move on to commissioning. So you need to be lined up for, if you did the torsional analysis and it said that you needed to do testing to confirm whether you're safe or not, make sure you do torsional testing during the commissioning process, validate the changes in the retrofit design. Also, a lot of we usually recommend having an owner's engineer on site during installation just to oversee the process, make sure that everything's going all right as a technical check around the process, make sure there's no startup issues on commissioning, support that commissioning process. You're typically going to get involved into some kind of formal performance test, whether it's PTC6 or otherwise, whatever's negotiated up front with the OEM, to dictate and say, hey, was this performance guarantee met? Was this project meeting the goals that we agreed to? And one of the important parts is correction curves, because the correction curves are basically, to hit the exact point, it'll be slightly different, when you're running it in real time. So the correction curves are what are used to adjust the point against the performance guarantee. So making sure that both parties, both the OEM and the owner, are in agreement, up front, so that everybody's on a fair slate. And then usually, we get involved sometimes on independent evaluation of performance test data, but you can do your own performance test data if you have in-house expertise. Compare it to your contract requirements. Are you in agreement and everybody signs off that, yes, we met the performance, or no, we didn't, right? And then, having engineering backup from your team or third party, for any anomalies or issues you find during this initial startup, so that you can vet those issues or figure out a game plan on what needs to be completed so that you have a successful startup, a successful commissioning. So that kind of recaps, the process, the turbine, the generators, kind of our overview. I just have one real quick slide in here for those of you that some may work with us regularly, some may be less familiar with our group, but we are part of a power generation group. We have TG Advisors in our wing. We have an automation team and Kestrel Power Engineering. So I've got a list of just some of the services our teams offer for Uprates, from control systems to planning to design reviews and so on and so forth. So definitely, if you guys ever have any questions, feel free to just shoot us an email. We're happy to answer questions, or if you need any additional support through your retrofit or uprate processes, we're definitely here to help. So at this time, I'll open up the webinar for questions. You also have our contact info here. If you have questions that come up afterwards you'd like to ask, feel free to shoot Tim or myself an email. We'll be happy to reply and answer your questions. So we'll open it up for questions. All right, doesn't look like we have any questions that have come in. So with that, we'll end the webinar here with 1 minute to spare. Everybody have a great day, and thank you for tuning in. Feel free to email us if you have additional questions that come up after the webinar. Thank you, everyone. Bye.